end. And so I'll be talking about this electromagnetic perspective to the analysis and design of MIMO antenna system for 5G and beyond. So I hope that I am audible. In case there is any issue, I will like request Kirtipriya or Mahesh, Dr. Mahesh, to just inform me so that I can try to resolve it. So as you can see, this beautiful workshop that is consisting of speakers from several backgrounds from industry and some of the veterans of our like field. And the main theme of this workshop is basically on 5G. And as I thought that from antenna engineer perspective, we should be talking about a little bit on the antenna technology, multiple antenna technology that has actually revolutionized the communication systems from 1G to 5G. So MIMO, that is multiple input, multiple output, that is one of these key enabling technology for the 5G. As we know, before 5G, also for the 4G long-term evolution, there was MIMO, and now we are expecting the MIMO to be in much bigger scale. And also currently we should be aware about that we are currently on the process of going towards 6G in terms of research, and a lot of groups both in industry as well as academia are looking into that. Now, myself being from an antenna background, I thought that I would provide some electromagnetic perspective to this analysis and design and of these MIMO antenna systems. So electromagnetic perspective, by that I mean there will be some of the proliferations or some of the amalgamations of concept with computational electromagnetics as well as analytical techniques to evaluate certain parameters for these MIMO antenna systems as a whole. So I would start by giving, I think, see my slide change, it's slightly delayed. So I will start by some discussion on the evolution of 0th generation to the 5th generation and why this MIMO is needed. Then I'll be talking a little bit about some of the insights on this pattern diversity MIMO antenna design, some of the works that we did and we are currently doing. I will be talking about that. Then I will discuss about the later part, that the electromagnetic aspects, both computational as well as some of the analytical framework that we will be using in evaluating these MIMO antenna system parameters. And finally, I will touch upon some new technologies for the 6G implementation and also some of the research that I am doing, and several of my peers in IISc and other places in the world, they are also focusing on that technology. So I hope I have around about 1 hour for the talk. We can probably have some discussion. So I'll try to move fast with the main content, and I can maybe take up some questions and discuss about the various issues. So before, I thought that just instead of making it a like a simple boring lecture, I will just take you through my own journey a little bit, and I'll just like collected some of the snapshots from my undergrad life. I did my undergrad in Jadavpur University, and this was almost 10 years back. And after that, I went for the graduate studies in IIT Kanpur. So there I did my master's and PhD. So I worked on this multi-band and wideband MIMO antenna system design, and I worked on the implementation part as well as the characterization part in far field and near field. And after that, I like went for some international visit and postdoc to Royal Military College, Canada. So I did some part of my PhD thesis in collaboration with RMC, especially the group of Professor Yahya Antar, who is currently the IEEE AP President-elect and will be President next year, and he is an IEEE Life Fellow. So it was an honor to work with him and his group. So there you can see some of the snapshots that it's basically this time of the year, it's snowing, and maybe like the temperature is also much below like in the sub-zero level. And the experiences that I gathered in both RMC and during my PhD helped me to right now work towards my current goal, and I am trying to set up like on the process, and I have like established the main funding and all those things for the laboratory for this innovation and development in antennas, radars and electromagnetics in ISC Bangalore. So it is an IDEA laboratory, and you can like I have provided the web link to that, and you can probably like visit it and see it for like if you have some more queries or any interest in joining our group, because we are actively looking for PhD students and research fellows to join our group. So you can see in this figure Professor KJ Binoy, who is currently the chair ECE in ISC, and Professor Ananthanarayan Chokalingam. I'll talk about him a little bit later, while I'll be discussing a little bit about the massive MIMO or the large MIMO systems a little bit. So in some of the snaps that I joined in last 2-3 months, so I've taken some of the snaps, and people who are connected to me in social media, they might have already seen this kind of stuff, that the garden and the main building and the ECE building. So some of this I take with my cell phone. So with that, I'll now come to the main agenda of my talk, where I'll discuss more about the evolution of this cellular communication technology, mostly from users' point of view. If you look into it, you can see that we started with these military grade portable AM and FM radios back in the 1940s, and now we have the present day smartphone. So which is in the like at the beginning, at the onset of the technology, it was mostly about the voice communication. But now we have voice, we have data, and by data we mean not only like file transfer, message transfer, and also we are connecting to live audio streams and video streams. And if you see that in these current pandemic times, the amount of these webinars and the online events, especially I'm talking from the academia point of view, that these kind of events have been happening all throughout the globe. And this is made possible mostly due to the advancement that has happened in terms of this cellular communication and wireless communication technology. So as users, we are being benefited, and we can now disseminate information and exchange ideas, and it has led to this global connectivity. So from a technology's point of view now, what actually changed? So before going into that, just a little bit about the history. We talk about 5G now. So the question is, when did it start? So the start, if you see it, you can the word we use, a mobile telephone service, but and we mean mobile smartphone, a small device that we can put into our pocket. But if you see the first mobile telephony service, it was not about the smart phone. It was about like connectivity between these various vehicles, let's say for some healthcare or some goods transfer kind of stuff. So in those vehicles, the intervehicular kind of technology that had some of these devices that was introduced by Bell Systems. So I've collected this figure, and it is basically now people nomenclate it as this zeroth generation of this mobile telephony. But now, if you look into the first generation, then that is where you see the portable cellular phone that was introduced by Motorola. And one of the figures that I have collected over here, a businessman using the Motorola Dynatac 800X for this portable, some of these, like maybe talking to his colleagues or something. So the evolution from 1G to 5G, if you look into this slide, you can see that over these past years, there are various stages like research and standardization of the technology and the commercialization. So the commercialization generally follows after the standardization and the research part. So we have evolved in terms of these user end, like the devices. We have now the data and all those things enabled, and we look into 2G and 3G. So I will not go into like all the details, but you know that this global system for mobile telephony and the GPRS, we all experienced it. Most of us in our generation, we experienced the use of the 2G for like texting to our friends, and maybe at some point of time we used it for accessing some video, like when the 3G and came. And now in 4G we can have all these YouTube and Facebook live streaming and all those kind of stuff. So we are looking into the 5G now. So from engineers point of view, so when we talk about putting into more and more data in the system, we are essentially looking into the channel capacity, and enhancing the capacity is one of the main goals. Like I'm trying to talk in very simple colloquial kind of terms, but apart from the capacity, another issue we have to be aware of is basically the coverage. So the coverage is basically taken care by the lower frequency of the system. So if you look into the current ecosystem that people are trying to think about is to ensure the coverage to go below, we need to go below this 1 gigahertz or the 6 gigs kind of like sub 6 gigahertz kind of frequency range. And there, essentially, since in the lower frequency side, we are having the larger cell size. But when we go into the millimeter wave frequency range, 30 gigs and the higher millimeter wave bands, so essentially we'll be looking into very small cells. So, and also there will be issues with the atmospheric absorption and all others kind of stuff. So basically what people are trying to think is this, use the sub 6 or let's say sub 1 for getting the better coverage, and use the millimeter wave frequency bands to ensure or to in a way replace the some of the like fiber optic connectivity or maybe that backhaul kind of thing. You can essentially use the millimeter wave frequency range to take care of those situations, and maybe an indoor office kind of environment, those kind of connectivity. But if you look into a large rural connectivity, as some of the researchers are working to use the TV white space to cover, from an Indian perspective, I'm talking about that, where we have in many places we don't have the like fiber optic kind of connectivity, but we can still have some coverage, and we might not ensure high data rate, but there we can at least ensure some of the basic facilities. So at this point, just 5G is not always about the data rate. So that is one of the point that I was trying to make here, that it has several goals under its umbrella. And if you look into any documentation dealing with this 5G new radio, you'll have that it is basically having these three goals. One is being the enhanced mobile broadband. That is basically with the data rate. But there are other aspects also, like the mission critical control and the massive Internet of Things. So in EMBB, or this enhanced mobile broadband, we have this extreme capacity like 10 Tbps per kilometer square and multi Gbps peak rates. And also we have this ultra, like this high density that again comes into this massive Internet of Things. If you talk about the mission critical control, we have to go with the high ultra high reliability and ultra low latency, these kind of things, and also extreme user mobility. So these are sometimes this mission critical control is ultra reliable low latency communication that is talked about. So sometimes some of the things might not need, like let's say this massive Internet of Things, there we might not need very high data rate, but we need ultra low energy. For this EMBB set of the side will high data rate. So there could be like some of these issues where we need to like just rethink our point of views, and not always about the data rate. But today, in today's talk, I will be mostly focusing on the technology that is mostly related to this EMBB side of the things. So this is another hyper service cube taken from another company a white paper. So here you can see that the links per kilometer square is there, and delay per millisecond is along another axis, and throughput is along another axis. So with that, we are basically looking into like a complete system overview. Now we are talking about, I will be like talking about the MIMO as a MIMO antenna system, how it works as the enabling technology for these future networks. So what is the motivation for use of this multiple antenna system? So that is the question. And you can see that the data rate is continuously increasing, and our applications and our like devices are becoming more and more data hungry. So from the knowledge of this Shannon channel capacity, we know that if we increase the available bandwidth, then we can you increase the data rate or the channel capacity in a certain way, or at least ensure the error-free communication. But we cannot have a control over the bandwidth as our wish as engineers. So we have some of the limitations on the available spectrum, and the International Telecommunication Union has approved certain kind of spectrum for the 5G, like the sub 6, as I already mentioned. Sub 6 is there, then sub-millimeter wave bands are there, and the upper millimeter wave bands are there. And they have certain different application areas as well. But the bottom line is we cannot increase the bandwidth of our devices as our wish. Not only the availability of the spectrum, but also designing the various components for that kind of wideband is sometimes an issue. And we have to not only design the antennas, we have to design the matching circuits, we have to design the backend circuitry. So they have their unique challenges. So the takeaway point is we cannot go beyond a certain availability above the bandwidth. So that part is gone. Then we can again think about that, okay, we can boost up the signal to noise ratio by boosting up the transmit power, let's say, but that is again have to be limited for the safety requirements, and it has to, we have to work together for the greener and safer communication systems. And regarding the modulation schemes, so modulation schemes also we cannot go beyond certain higher order. So then engineers thought about the technique for where we are basically going to have a unique solution that at the transmit end and the receiving end, let's say in the base station or your mobile device, will enable it with multiple antennas. The base station also will have multiple antennas. In your device also will have the one main antenna and several other diversity antennas. And using that, using the signals from all these antennas, we'll try to use several signal processing techniques. We can use the transmit diversity and the precoding kind of stuff in the transmit side, and we can use like this maximal ratio combining or switch diversity, several kind of things. And then we can use this zero force precoding kind of stuff to basically get or go beyond, work beyond the limit for a single input, single output communication system. So people have shown through several rigorous mathematics and also through experiments that by using this kind of multiple antenna technology, we can essentially work around the capacity, and we can actually boost the capacity by decomposing this multiple antenna channel into several parallel single input, single output sub channels. So I like now I'll come to some of the antenna aspects of this thing. So personally, I have had some of the research experience on this antenna design during my master's as well as during my PhD. And we all know, I hope that in the audience we have quite a number of people who have worked considerably in the antenna design part. So there we essentially have to like go through this in a nutshell. We can say that we have the S parameter analysis in the vector network analyzer, and we have the radiation pattern measurement in the anechoic chamber, and also there are other stuff that follow. So some of the antenna we designed some ultra wideband monopole antennas and arrays, and also this MIMO. So I wanted to show you this figure to just point out that let's say the basic difference between an array and a MIMO antenna, because whenever I talk in some podium, this is one of the questions that follow. So you can see that, let's say in the left hand side we have a very conventional and simple array where we have a like main feed line, and it is branching out by using these power dividers, and it's exciting all these CSRR loaded dipole elements. So, but here the point is we can calculate the far field radiation pattern by using the knowledge of this element pattern as well as the array factor. But in this case, we do not have that kind of an array factor kind of knowledge. So because the elements may not be having oriented in such a way that can give you, because the polarizations will become different. So that is one of the main challenges that we have to basically distinguish between the MIMO and the array from an antenna point of view. I'm just telling. And here we can access all these ports in all the elements. But here we are basically going to put some of the phase shifters or something if we want to make it an active array kind of thing. But we might not have an independent access to all these ports over here. So with that, I'll move on. And so just discuss about some of these pertinent issues that we generally face during a design of a MIMO antenna. So this is a generic MIMO system viewpoint that I wanted to put here, that this is the transmit side and the, let's say, empty number of transmitters and MR number of receivers over here. In between we have a channel. And here in the back end, we have the sources and the source this impedances over there and the load impedances, and there we'll be collecting the signal and maybe doing the processing. So from the electromagnetic viewpoint, this is the general system model. But what are the main design challenges that I'd like to point out, and this might be helpful for any PhD students or master students who might be working in this area, that we need to look into this conventional antenna aspects definitely about the impedance, bandwidth, gain, side lobe level, front to back lobe ratio, all the things that we learn from our textbooks. So those things are definitely relevant here. But apart from that, we also have to look into some of the additional issues more carefully. One being the footprint reduction, like to achieve the multiband wideband performance within reduced electrical size of the antennas. That is one of the big challenges in terms of the square of operating wavelength. We have to ensure that the footprint is small, of the entire system is small, not only the individual antenna but also the complete system that is built by the antennas, let's say in the transmitter side or the receiver side. But again, there is the challenge that you cannot have anything for free. So whenever you bring the antennas closer, you are going to increase the mutual coupling. So to reduce the mutual coupling, again, there are certain technologies like the neutralization lines. You have the electromagnetic band gap structures, deflected ground structures, stuff like that. And also, not only in terms of the port coupling, we also need to ensure that the patterns of the antennas, their correlation, which is basically defined as this envelope correlation coefficient, like quantified by this coefficient, for specific propagation scenario, that has to be ensured below a certain level. So this is very important because we mentioned this term specific propagation scenario. It might not be that we are always operating in a uniform propagation environment. We might have to work in a different environment where the signals are coming from a certain direction, and it has certain probabilistic information about that there could be some power gain over one polarization to the other. Like we know that there are two orthogonal polarizations, so there might be some power imbalance existing over there. And also there might be some directional bias, like from certain direction we are having the signals coming. So then we need to join our hands with the communication theorists, and we need to have the information about the propagation scenario, and that information has to be fed into the design of the antenna system. So this is very important, that if you want to work on the MIMO antenna design, then you cannot only think about the antenna part, you have to also think about the communication and the implementation part, the particular propagation scenario, and that will essentially help you to build better systems. So without that knowledge, you can build systems, but that might not be optimal. If we want to build the more optimal system, we need to integrate our knowledge about this both the antenna design as well as the communication system. So I thought that I would just present some of the antenna development in the handsets, because that is something that we all have with us. And despite several technical glitches, we have this these mobile phones and all those things as integral part of our daily life. Sometimes we are we work a lot with the cell phones to get some data or something like that. So but the question is, from technology point of view, what is actually there? So if we see that, if you go back to this 1980s kind of antennas, this Motorola Dynatec kind of system, so there we basically had this kind of sleep dipoles as the radiator. There was no MIMO business. We had a single antenna, and you can see that from a technology point of view, it is basically just extra protrusion of this central conductor to a certain length. And now to get a proper way out around this unbalanced current kind of stuff, balanced to unbalanced transition kind of thing, we use this sleeve. We know that sleeve from our shirts that we wear. We use sometimes we fold the sleeves or something like that. So this is you can imagine this is the sleeve. So I'm just trying to talk in very simple terms instead of going into the details. But now if you open up any cell phone that you have, or this is probably from some time back, but here you can just included this figure to show you this main antenna over here that is working in the 900 megahertz and 1800 megahertz. People with the knowledge about the GSM will know that these are the specified frequencies, and it is pretty obvious that this like larger length conductor, this is responsible for the low band arm, and here you have the high band arm which is at the 1800 megahertz. So this is the dual band inverted F antenna working as the transmit receive. But apart from this, you have this diversity antenna. So diversity antenna, this is basically called here in this case, it is the spatial diversity, because in terms of the spacing, there is some difference, and when that difference exists, we basically ensure that these two antennas are not talking to each other that much. Now, how does that help? So I will try to explain the concept of MIMO in a very simple analogy, that if you have you can tap into this like several multipaths that are actually bombarding into your cell phone, then with that thing you can basically combine them using maximum ratio combining or maybe switch diversity, and that information you can actually use for getting enhancement in the data rate. Now if you have the single antenna, then that fading could have been like detrimental. But now by using several multiple another diversity antenna over here, we are basically using that fading thing to our advantage, and we are essentially boosting up our effective channel capacity. So that is something that we do with the diversity antenna. And how it happens, to understand that, you have to look into how the channel is now conditioned using these two antennas. So instead of one thing, now you have to consider the like number of antennas in the base stations also, and then you will get a channel matrix, and from the knowledge of the channel matrix you will know that how this rank of the channel matrix is becoming. So again we will enter into that mathematical and on all those domain. So if we ensure that the number of singular values and the channel strength at all these singular values are like uniform or having a proper conditioned state, then we will get certain enhancement in the channel capacity. So something like that is very if you look into the backend signal processing, it has a lot of things. But like in terms of very simple antenna perspective, this is the spatial diversity, and we need to accommodate these antennas properly so that they do not interfere with your like placement of hand or placement of the phone close to your ear, something like that. So you have to think about all those aspects. And not only that, we also have other integrated antennas. So there has to be like ensure proper like energy exchange or kind of thing, that shielding kind of thing that has to be ensured by us again. So these are the some of the aspects that come into business there. And apart from the spatial diversity, we also have the concept of polarization diversity. So here you can see the two inverted F antennas. You can probably, I'm trying to put my marker over here to just show that this is one horizontally polarized antenna like this, and this is a vertically polarized antenna. So we are having a polarization diversity kind of system over here. And that again, that ensures that if you have orthogonal polarization in very, like you can see that the distance here is much larger, isn't it? And but if you see here, then the distance is very small, because if you have the orthogonal polarization, you will have this very less port coupling kind of thing. So these are kind of electromagnetic knowledge that is imparted into building of these systems, and I am not even going into that part, because that is mostly taken care by other engineers. So it is not only the business of the antenna engineers, all the engineers in various like electronics and communication fraternity and computer science fraternities come together to make this a small device that we are now using so prominently in our daily lives. So how we are looking beyond that, like when we are talking about this integrated 4G, 5G handset antennas. So some of the groups like Professor Desmond Sim and so many other groups, and we are also now jumping into the trying to jump into the fray, that they're trying to build these multiple antenna enabled handsets, and T-Mobile and some of the other companies, as I read sometimes in the news. That's when we put you can tap into as much as the system in the receive system. Let's say your base station is enabled with 10 antennas, but your receiver has only 2 antennas, then your effectively your channel will be 10 cross 2, and you'll get two like this singular value kind of thing. But if you increase the number of receiving antennas over here, then you will essentially increase that data rate. If for keeping the base station number of antennas fixed, now you can basically increase the data rate by increasing the number of receive antennas. So That is one of the key things, that we have to put all those diversity antennas around the phone, and then we have to ensure the mutual coupling is minimized, and we also have to take care of the SAR levels and all those things. So these are some of the challenges that are here, but I wanted to show the technology. And since why I mentioned that boosting up the data rate kind of thing, so I thought that just a little bit about the mathematics from this chronicle channel model point of view. So for completeness, so in case of single input, single output, we have a one transmitter and one receiver over here, and our channel matrix, or not matrix in this case, it is basically a scalar here. So that is H scalar value over here, and we can see that this is clearly the normal thing that we learn mostly in our undergrads, as when we talk about the Shannon channel capacity theorem. This is the signal to noise ratio. PT is the transmit power, and this is the noise variance over here. And now when we go into a multiple antenna enabled system, so we have empty number of antennas, as I said, and MR number of receive antennas over here. So our channel matrix H, that will become MT cross MR. And then this H is not the channel matrix. This is, sometimes it's slightly confusing, because this is basically the Hermitian operator over here. You can use some other operator notation also. So basically what we are trying to do is, now we are using this H into H Hermitian kind of thing, and dividing the, like, this is a water filling kind of algorithm, can be there, other algorithms are there. So now this is the total channel capacity. In short, in a nutshell, this is the channel capacity for the MIMO system. Now for this to be greater than this, there are certain conditions that this H has to satisfy. So to analyze that, people look into the channel model, and this is one of the popular channel model, where we can see a couple of things. Why I put this, because to try to point you towards a very important aspect, that the central term you see, this HIID, this is the IID Raleigh wireless channel. So here the entities or the entries of this IID matrix, they are basically independent, identically distributed Gaussian random variables. But when we talk about these two terms, so this is a kind of stochastic part, but the deterministic part comes from the interaction of the antennas. So we talk about this psi r, that is the receive correlation matrix, and psi t, that is the transmit correlation matrix, that is basically quantifying how these two antennas are talking to each other. So that can be through the near field coupling, that can be through the far field correlation. So all these parts will be, all that information will be actually compact and packaged in this co-correlation matrices. So that knowledge from an antenna engineer point of view is very essential. And because we can reduce these parts very less if you keep the antennas far apart, but because we have to keep the form factor of the system very small, so we have to now analyze that part as well. So now I will just discuss about some of the antenna design aspect that which I did in my PhD, and I am aware that several other groups are also working on similar kind of problems, where that rotational symmetric arrangement of the elements is considered. So this is not for the cell phones, this is mostly for the access point kind of application, and where we are targeting this coverage of this sub-6 gigahertz bands, as well as the backward compatibility and overall compact footprint, peak gain of certain value, and isolation greater than 10 dB, and ECC less than 0.1. These are some of the specs that are with us beforehand. And now there are several design options. We can choose miniaturized multi-band elements. We can choose some of the induced lower frequency mode in the complete structure. So this was one solution strategy that initially we tried to adopt. We tried to minimize the antenna elements, and but then the better way to do that is to consider the complete system modes. Like when you place these antennas close together, there might be a lot of issues that are not happening when the antennas are in an isolated manner. So that can be done by the in situ kind of design, by placing the antennas in the complete system with the surroundings, and then try to optimize the antenna element pattern. So that is something that we did. And but just to let you through the design process, so the starting step could be like, we can take 4 simple dipoles, because dipoles we all study, I think, in the from Indian, for Indian audience, I can say that our GATE ECE syllabus, there also we have basically the knowledge about the Hertzian dipoles, and maybe a little bit about the half wavelength dipoles. So we can start little bit from the half wavelength dipoles and placing them together in an orthogonal fashion like this. and we can check that where the reflection coefficient is and how the mutual coefficient, mutual coupling coefficients are. And then we can see that it will provide some kind of diversity. But again, there are several issues with this, with the front to back lobe ratio and all those stuff. So later on, what we try to do is we try to implement those kind of thing in printed technology. And one of the way to do that is we can increase the ground plane and think of it as a CPW fed thing, or maybe as a printed microstrip feed kind of thing. I'll come into that in a moment. So slowly you can see how the design is evolving. So I'll come to the final structure for the sake of time. And so this is the one of the things that I thought, that if we use an inverted element with microstrip feed, and we can now symmetrically arrange the ground plane size, ground plane shape, and we can connect it for the DC kind of connectivity. And by that, we can again ensure a lower frequency mode is actually occurring over here. Like if you see that this isolated monopole, it will give you one impedance matching mode round about this frequency. But if you use this in a connected environment, then it will give you an additional mode. So in this letter, if you can, interested people can download it and maybe follow that. We ensured that how that frequency can be achieved, and what is the radiation mechanism from the currents and all. And we built the system, we measured the S parameters, and we went through the like pattern analysis for this before reporting it. Later on, we improved that structure a little bit. We tried to follow certain frequency bands which were not covered in the earlier, and we also tried to minimize the size. So these are the kind of challenges that we faced that time. We went through this 4-element MIMO antenna design for this 2.5, 3.5, 5.5 gig bands. And there we use this sub-wavelength resonator loading technology. People often call it this metamaterial inspired technology, but we tend to avoid that term because this is simply a resonator over here, split ring resonator that we put, and using that resonator loading, we can change the impedance matching characteristics of the antennas, and that's it pretty much. And we can now optimize the dimensions of this to make it cover certain frequency bands over here. So with that, we then not only that design, but then we have to, as I mentioned earlier, we need to look into the ECC for a realistic propagation scenario. So we did that, and we tried to ensure that the envelope correlation coefficient is below in a certain level. But if you can notice that for very narrow kind of beams and for certain angles of incidence, there are some increase in the ECC value. So these are the characterization that we did on these antennas. And while doing this characterization, we saw that there are several issues that are existing. Like we, from measurements, if we try to do that, then we need to have complete 3D pattern measurement. And that facility was not available with us at our time, and probably now it is there, but still it is pretty tedious. And to gather the, with even a small angular resolution, to get that kind of value is very tedious. So one way is from the commercial simulation softwares, but there also there was the technology that we use is basically we go for evaluation of the radiation patterns at the discrete frequencies, and then use that pattern knowledge and combine them into this expression that is present over here. I'll not bore you with the mathematics, but there is an expression that combines the radiation pattern theta and phi components, and the p theta and p phi values, like the incoming propagation functions kind of thing, cross polar discrimination. So everything is combined in that expression, and using that we get the envelope correlation coefficient. But that is also, we found that has certain disadvantages, like not disadvantage I would say, but it is basically, it numerically it is tedious to do. So one way to do is use the S parameters, but the S parameter based ECC evaluation that gives you the knowledge of the envelope correlation coefficient for only a specific propagation scenario, and that is the uniform propagation environment. So for that we did some innovations. Later on I will come into that, and use that knowledge of, as I was mentioning, the knowledge of computational electromagnetics and some of the analytical tools, and merge them to get some of the techniques to find out the ECC for this kind of antennas. But recently, in this year, we are working a little bit, although the work is stalled and somehow affected due to the COVID scenario, but we are working on developing some of the MIMO antenna systems for this 28 gigs and 38 gigs application. And this work we are currently doing with our like collaborators in IIST Trivandrum and also in RMC Canada, and some of these papers will be presented by the students in the like recent conference AppSim over there. So sub 6 gigahertz 5G antenna, mobile smartphone antenna system, that is also like it's taken up by one of the students, and he has basically used this horizontally polarized and vertically polarized elements, slot kind of elements, to make it work around this sub 6 frequency band. Some of the bands he chose and he wanted to make it operate. So we will be reporting these works pretty soon. So now, so far I am talking about the handset kind of things, but I now briefly talk about the base station antennas and what are the evolution strategy for these base station antennas for 5G. So typically, if you look into the specs for a base station antenna, these are taken from this paper by Beckman and Lindmark, Evolution of Base Station Antennas for Mobile Communication. So the power handling and the sector coverage, this is one of the big thing. And also the base station antenna use the concept of diversity, and to be more specific, the polarization diversity, to combat this relay fading, because the base stations have to capture the signal from the users from different directions, and there is always multipath and all those things are there. So like we went other way around, like we talk about diversity in our handsets, but actually our base stations have been using the diversity for from pretty like long time. But now what is the idea of this massive MIMO that we are trying to look into, put a dedicated transceiver integrated directly to the antenna elements. Let's say this is a slot array that is present over here. We can see that there are several of these or like mutually orthogonal slot elements represented by two different colors. So now if we can access all these elements, so we can basically control the amplitude and the phase control of the entire aperture. But again, that might be a very beautiful or lucrative concept from from a communication theory point of view, but we have to also assure ensure properly this economic aspects as well as the manufacturability, how we are going to do that, heat management, several other issues are there. But the concept from an antenna point of view is basically an active phased array kind of thing. You can think of it as there will be beamformer, then there will be this radiating aperture where we are going to have the maximum phase control. So some of the work, if you look into this massive MIMO now we say, but I think the name earlier, which some of my senior colleagues in ISC, Professor Chokalingam and Sundara Rajan, they worked on this, and this is one of the books that they wrote on this large MIMO systems. And this news was reported, I think it's back from 2016. So for any candidate interested in knowing more about the like signal processing and the communication aspects, communication networking aspects of the MIMO system, I'll suggest this particular book because it is a beautiful read. Now, in terms of very simple way, like what is gained, people can ask that what is gained while we put so many number of antennas in the base station. So one of the advantage from a downlink perspective is this beamforming. You can see I was trying to show the contrast between a 4G sectorial and 5G kind of massive MIMO antenna. That here you can see that the beams, mainly we are having this control over the azimuth coverage, but in the elevation, the beams are quite broad. But now, since we are having a very great control of this entire aperture, by having this large number of elements, we can also ensure very narrow beams, and as well as we can achieve this total elevation beamforming as well as azimuth beamforming, so a full dimensional beamforming. And there could be some of the stationary locations, some of the mobile locations, all those things that can be having a very beautiful control if we have that kind of a large active phased array in our base station. But again, there are concerns that, well, if we put so many number of antennas, so are we basically pumping in more power? But that is not actually the truth. In fact, that is the converse. And if we have large number of antennas, then we can ensure that we can work on the system by in a lesser power requirement. So essentially the power that is needed for the base station, that will also come down. So that is one of the key aspects, that when we are increasing the directive gain, it is not the amplifier gain, it is the directive gain of the system. So we are, if we just bring down the power level over here, then you can actually, and then what advantage that makes this kind of directive beams is basically you can remove the signal to interference noise ratio, SINR kind of thing. So that kind of thing can be brought down, and we can pinpoint to locations, and but essentially we can also reduce the power that is needed at the base station. So that is the one of the advantage of the massive MIMO technology. So some of the test beds that people have built, and in Land University, this is one of the figures that to explain that various processing layers like this control processing and this centralized processing and the distributed processing, where you have these switches and these software defined radios and this array of antennas over there. So array of antennas, they have only this patch kind of elements over there as in the front panel. But we in this figure, just to show you some analogy, like this particular figure, I was trying to show that, okay, we have this full dimensional coverage. So just to correlate with that, I am just showing one of the turning torso architecture that is used for the massive MIMO, and interested people can go into this paper, this stacked patch antenna with dual polarization and low mutual coupling for the massive MIMO application. So this is the turning torso architecture. Why it is named such? That we have, you can see that each of these layers of these arrays have a certain kind of twist in between them to get lesser mutual coupling between these various stages. So how this complete thing is made, if you go for piece by piece dissemination of the entire thing, then you will see that there is one unit. This is the unit which has 8 ports over here, and this individual like 2-port kind of system that is basically making up by this 4 patch antennas. So the way it works is this dual port system over here, this is the smallest building block of this complete system. So one of these ports that will give you the vertical polarization, and one of these ports that will give you the horizontal polarization. Details is given in this paper, but the way it works is if you excite one of these feeding structures, then basically it interacts with some of these slots that is present in the ground plane, and some of the coupling strips, and essentially it excites all these 4 patch antenna elements simultaneously and gives you a very high directive beam, and that is obtained for 2 polarizations, one for the vertical using this port and one for the horizontal using this one. So using this 2-port kind of unit, first they bring this make this like 8-port sub module, and this is one of these module that is placed over here. Let's say C1, C2, C3, C4, these 4 2-element units, that is one of the modules, and then that is again twisted, like placed in this 6 kind of element kind of fashion. So the idea is you need to have the full azimuth coverage, but at the same time you have the full elevation kind of coverage, and you have, if you count, that there will be around 144 number of ports for this particular system. So when you have that kind of control over the total phase aperture for this cylindrical kind of coverage kind of thing, so that will give you a lot of advantages in terms of the signal processing also. So real life testing for this kind of system that involves like indoor testing, and multiple antennas are used over here, and the base station can be placed. This is the indoor testing. Then outdoor testing also there are. So I will suggest interested people to go to the Land University web page, where they have all these details on how these things are tested. Now we are talking about the downlink so far, like the how the base station will communicate with the these various number of users. But we also have to think about the uplink, like the user will first send some signal pilot maybe, and then so for all those details I have just put the reference to this book, and Professor Emil Bjornsson, he also has several of his YouTube lectures to explain this kind of concept about the implementation of massive MIMO, uplink and downlink on this kind of stuff, and spatial correlation, that is also a critical issue for the massive MIMO. But I will just come to again the antenna part, like when we talk about the spatial correlation in these multiple antennas that are present in the base station, like so far I was talking about the antennas in our handset or the access point, but again the antennas that are several number of antennas placed in the massive MIMO base station, that will also have some of the interaction, and the interaction can if you want to reduce the form factor, then again that will be in the near field. So this is a very rich research area where we look into assessing these various antenna aspect in terms of the MIMO channel modeling. We look into the effect of the directive antenna patterns, we look into the effect of the relative polarization as well as the inter-element spacing, and these non-planar spherical wave fronts So this is in summary that some of the work that we do at RMC and with our some friends, that we basically reconsider these antenna aspects of MIMO system and try to improve the existing channel modeling schemes. So for one of the key things is I come into that point because that is a key aspect of this MIMO system design is the correlation. And I already talked about this part, so I will not take too much time. But again, I like to point out that it will consist of these theta components as well as the phi components of the radiated fields, as well as some of these propagation parameters, the statistical and angular probability distribution and the cross polar discrimination of the incoming wave, and some of the to calculate this ECC between these various antennas. But now, since we are talking about this interaction of the antenna elements in terms of the patterns, so I would like to dive more deeper into the computational aspects of these things. So I'll talk about the computational electromagnetics, the knowledge of the CEM that is needed in modeling this kind of system. So just to briefly show you that the process of modeling interaction of EM fields with the physical objects and the environments is basically what we mean by this computational electromagnetics. So it is needed to assess these antenna circuits and systems needed for the radar cross-section analysis and the EMI effects, as well as the bioelectromagnetic problems where we compute the specific absorption rate. So there are several CM techniques we know, and I think some of my preceding speakers will succeeding speakers, they will talk about this CM, that which kind of environment needs which kind of simulator. If we want to simulate a large system, we might need something. If we want to simulate a very small system with some complex complexity in terms of the cells and the complexity in terms of the dielectric constant, then we need some other solvers. So FDTD is one of the things that I worked on. So I'll come to that and how I applied this thing. So why we need this FDTD kind of things is because see, when we try to model the antenna currents to assess the correlation between these antenna elements, we cannot do that using a very analytical expressions, because we are essentially working with several complex structures, printed antennas, where the currents are not always can be modeled by simple analytical expression. That can be done for simple antennas, but for complicated solutions that is not possible. So something that we can say that the earlier developer of FDTD, Professor Ken Yee, he actually pointed that out, that solution to this time dependent Maxwell equation are unknown except for a few special cases. But at that time, the memory capacity of the computers of his time, which he mentions as the present day, that is now boosted several times for our age. So we now have the luxury of modeling the system with much better precision. So basically, essentially, FDTD is basically, we try to, one way to look into it, we try to decompose this Maxwell's equation and apply them to a finite difference time domain way, like the continuous time and continuous space equations. They eventually, we discretize in terms of maybe some other time I can talk a little bit more about how these update equations are evolved. But the basic principle is, we use that continuous time thing and continuous space thing into a discretized way, and a staggered grid is there, and we try to update the fields to get some knowledge about the radiating currents and some of the other parameters, like we can post process it to find out the scattering parameters. So for the implementation aspect, I would like to point out to the audience that there are several books. So some of the books that I followed are here, like FDTD method by this Teflov and also by Sullivan. There are several other books also. So we need to look into the stability. We need to look into the meshing criteria. What is the best way to mesh the entire system? And then excitation and processing and all those things are there, like how to use the matched layers to eliminate these spurious reflections from the system. But now I'll come to again come back to why I talked about this FDTD, because our objective was to evaluate the correlation, spatial correlation between the several antennas over a wide frequency band. So to do that, what we used is, we used the integration between the FDTD technique and some analytical tool, that is this cross correlation Quinn system, that was introduced by Saeed and Professor Antar back in 2015. And you can follow this book to know more about it and more about the general spatial structure of fields around the antennas. So using this knowledge of cross correlation Green's function, you can actually evaluate the correlation between multiple antenna elements without actually evaluating the radiation pattern. So that is one big advantage, because we as antenna engineers, we like to play with the currents. We like to manipulate the currents on the system by introducing several structures based on our physical knowledge and interpretation. We sometimes try to suppress the cross pole, and similarly several other, like we try to suppress the mutual coupling. So one of that part is using the correlation. So when we have the knowledge of the correlation from the antenna currents using this CGF, then we can actually use that and integrate that with the FDTD technique to have the evaluation of correlation coefficient for a wide frequency band. So I know that is a lot to digest, but I am just trying to point out all those things so that interested people can take that up later after this webinar is over. So some of the work that I did was during my PhD, where I worked with integrating this cross correlation Green function with FDTD for this fast computation of ECC for wideband. So there are several algorithms. One of that thing was this FDTD-CGF that I reported, which used some of the time domain processing of this current and using the knowledge of CGF and the angles and using the Fourier transform. And one of the offshoots of that work we reported in transaction communications back then. And we did like benchmark all our algorithms by, I had developed a in-house FDTD code at that time to get a better feel about the currents of the system. So, but to do that, we needed to first benchmark that using the HFSS and see that whether okay that is actually calculating our scattering coefficient like S parameters, scattering parameters in a proper way. And only then we moved into using our algorithm for evaluating the correlation in wideband. So the beauty of this algorithm is we use the time domain currents generated by FDTD and then sample them out and use that knowledge, do some post processing using the knowledge of CGF, and then get back the correlation. So it goes basically in two shots, and we don't have to evaluate the radiation pattern for all the discrete frequencies. And essentially this is just as simple as calculating a Fourier transform kind of thing. So we use several like examples we took at that time, like we use triple band antennas and also printed antennas to show that how we can use the equivalence principle to find out the slot currents, and then use that to some printed antennas also. And recently, but all the correlation that we discussed at that time, like the correlation that we calculated from the antenna currents, that was for the far field. But then we looked closely into the near field of antennas. Now you can ask why we need this near field, because if you see the way the 5G is progressing and we are looking into several like ultra dense network of the multiple antenna systems. So there essentially you need to have some evaluation of the near field correlation of those antennas. In an indoor environment, we are not always running away to the far field. We have to think about, or we have to rethink our strategy to evaluate how the antennas are talking to each other in the near field aspect. So we introduced this term, this near field correlation, and reported this thing in the AWPL sometime last year. And we showed that how this correlation coefficient for the electric field and the correlation coefficient for the magnetic field will be different, and how to evaluate that using knowledge of FDTD, using correlation sphere kind of thing. I'd like to point out here that FDTD is not the only tool that can be used here, but we use that to evaluate the wideband near field correlation. So these things will be unequal, because in the near field, we do not have the beautiful relation between the electric field and magnetic field, the way we connect that with a simple plane wave kind of equation. That does not exist in the near field. So we also showed that by using an example where we had two dipoles, and we used a correlation sphere around it to evaluate the fields on these points using FDTD, and then we evaluated the far field correlation coefficient, the near field electric field coefficient, correlation coefficient, and the near zone magnetic field correlation coefficient. So you can see that how these are in stark contrast. So that is a way to we have to somehow go beyond our conventional knowledge, and we have to rethink our strategies in evaluating correlation. So some of the work is like we are currently doing on this near field correlation. So now all these are good, but we have to also, from an Indian perspective, we have to look into how the 5G initiative is there, because again we have to come back to the reality from the antenna design and all those things. And 5G initiative is one of the things that you can like I just tried to put this resource over here so that interested people can look into this. And I think one of the organizers of this talk, Kirti Priya, she has worked in this project for some time, so she will also have knowledge about this. But for the general audience, I wanted to make this that to with the view to develop the ecosystem for 5G mobile technology. The DOT, they have come forward this project, and this is supposed to be over by I think next year, and then probably we'll look into 6G. So ISC, IIT Madras, and CWIT, IIT Delhi, Kanpur, and IIT Hyderabad, and SAMI Chennai, they are also working together for this. So there are several milestones for this, like in terms of sub-6, in terms of the millimeter wave, V2X, like vehicular communication, and also the visible light communication. There are several milestones. I will not discuss about them in detail, but you can have a look into the website. So some of the topics to, I'll just try to wrap up my talk in 5 to 6 minutes. So with the 5G technology being there, and several players are trying to contribute over there, we are now also looking into some of the advanced techs that will probably take us to the 6G. So one of that thing is this cell-free MIMO system. So some of the papers are over here. So the cell-free MIMO system, most of the work so far is theoretical, and they are using the single antenna kind of access point. But some of the work that we plan to do in our idea lab with on the cell-free MIMO system regarding the implementation and also the processing of the system. So the idea is the general way we model the entire region with several cells. Instead of doing that, we are going to have a this is kind of a static arrangement, but we might have a dynamic kind of configuration where these are probably going to be connected by high-speed fiber optic links. And now a combination of these several access points that might work as a dynamic cell for these several users. So we will have the way to reconfigure our access points and do the backend processing in a way that our cells will be dynamically reconfigured. So this is a distributed kind of system, not a like like a system where a cell is here and a central base station. No, it is a distributed system. So these things are there. For details, so we can look into this literature and several other things. But another critical technology that I actually worked somewhat on was to use these reconfigurable intelligent surfaces. So just to briefly talk about that, how I came into that research, I was trying to model some of these uplink channels using my in-house FDTD code, and I was trying to actually emulate some of the results that are obtained by ray tracing. Definitely ray tracing solutions are much faster and all, but using FDTD and using the like systems that we have, we can do the cloud computing, so to bring down the memory and time resources a lot. So we can now look into the electromagnetic aspect of this things more closely using the FDTD. So that was my approach, and also to look into the near field modeling kind of thing. So using that, I used my own code to emulate some of those results. But later on, what I found out, and we reported sometimes last year December, it was published, that how to engineer the ion space structure of these massive MIMO links, mainly these pi links, we mean the uplinks, using these frequency selective surfaces. And we used some of these wire grid FSS, and these things was difficult to model all this coupling and all those things by some ray tracing code. But using our FTTD tool, we could go around that, and we used several like pointing flow plots for this sub-6 GHz regime, and we showed how the actually the channel eigenvalues are actually being manipulated by use of this frequency selective surface. So these are the results you can see probably in the letter. But at that time, I was became aware that this is one of the technology that people are looking into for the 6G. Like it is probably some unconventional thing, and for non-standalone 5G deployment, where we generally have an existing base station, we do not have like input it with multiple antennas over here, but we put an intelligent reflecting surface, and that intelligent reflecting surface is nothing but a reconfigurable frequency selective surface, where we can have a control embedded controller, and we can change the basically switching configuration, or maybe using some varactor or something like that. We can essentially, what we are trying to do is we are playing with the surface impedance of this thing, and now we are going to have some like beamforming control using that surface itself. So that has people have the communication community, they have reported that it has a lot of advantages beyond the standard relays, and it can bring down the power requirements and all those things. So there are some advantages, and some of the like survey for this, you can look into this thing. I think this is still in early access, but it is downloadable. So towards smart wireless communication using this intelligent reflecting surface. So the beauty of this thing is, so far when we have these passive reflectors, let's say a metal plate was there, then we do not have any control over that. But now if we have some control, then we can use it for the benefit of our communication system improvement. So I did some of the work with my collaborators in RMC and with SIDE also, that we developed some electromagnetic framework for this deployment of this RIS to control massive MIMO characteristics. And we presented this work in this year's European Conference on Antenna Propagation, where we envisioned that how you can use the various switching states, because the previous system that we reported was not just some frequency selective structure built near the base station. But now we have the model of this reflecting surface, and we proposed some of the schemes how to basically change these tuning states using some of the microwave technology. And some of my colleagues who are working on active FSS based absorbers, they already use this kind of technology. We can do that. So we plan to develop more on this in our lab. And finally, to little bit end little bit, because we are talking about MIMO and MIMO antenna and the electromagnetic concept. So I discussed about the development of 4-element antenna, and then talked a little bit about the massive MIMO antenna, then also talked about the channel modeling aspects, correlation and all those stuff. But we must not forget that since we talked, so we also did some of the fundamental research on this, and using our knowledge of FDTD and using doing some of the digging up of the old literature, and try to look into the directions where we can go in a more fundamental way for the representation of electromagnetic energy around antennas. So this is one of the work that is probably going to be out in magazine sometimes next year, but it is available in early access, this representation of EM energy around antennas. So interested people can look into that and maybe read. So I'd like to come to the end of my talk. Maybe I overshooted the time a little bit. I hope that's okay. So MIMO antenna system, I talked about this diversity beamforming and how various configurations can be realized. I also talked about how the spatial correlation estimation can be done, and how to use this FDTD based framework for the wideband correlation estimation. And then I talked about some of the technology for the 6G, like use of these reconfigurable surfaces to deterministically change the channel space. So with that, I would end this presentation, and I'd like to thank you for your patience and for listening to the talk. I'll be happy to take up any questions. Thank you.
Thank you, Dr. Devdeep. That was very interesting talk. So we'll move on to a few quick questions. So the first question someone has asked is, can you please suggest some simple method to evaluate the TARC? As you had mentioned about the correlation quotient, is there some other method for evaluating the TARC?
Okay, yeah. So it's a very good question. So TARC, well, the simple method, actually, I have seen through a lot of papers. The way people do is, it is not as difficult as for the FDTD, and it can be done for the on the measured S parameters also. All the thing that you need to do is, you need to basically as far as I don't have the slide with me right now for the expression of the TARC, but there is this you can change the basically phase of the S parameters. Like you can consider, like, not the S parameters will be fixed, but for the excitation signals, right? So B basically is the S multiplied by A. So we basically change the phase on the excitation signals, and that is basically randomized. So the way I used to do is, I used to run a code that will basically take the randomized phases, and it's very easy to do it in MATLAB. So you can take a number of iterations, let's say a Monte Carlo kind of framework. You can take a number of iterations, and using that you can basically generate a lot of excitation vectors. So your S parameter matrix is fixed. You generate a lot of excitation vectors using your randomized phases, and then combine them to get the B matrix. And once you know the B and A, I think the expression for torque is available as some of the summation over bi square and divided by summation over ai square. So it is not like you can do it for one iteration and that is one value. Some people do it, they take some discrete phases, let's say a 0 degree, 10 degree, 20 degree, some kind of values, and then find out the torque. But the best way to do is to take the randomized phases, generate a lot of values, and then average out the entire thing. So probably I think maybe the interested person can contact me and I can like share some of the details with that person directly. Yeah.
Yeah. So next question is, with the increase in number of mobile users, the beam switching may be complicated, especially when the movement is there for the user from one zone to other. So how is the situation handled, or how it is anticipated to be handled in 5G?
Yeah, so I think this is a very good question. And to be honest, like the mobile user condition and how to handle the dynamic beam switching kind of thing, maybe I am not the best person to handle this part because I have not worked on it. But yeah, I think the one thing that I would like to share from my knowledge that this basically the when we have this multiple number of antennas, so what I read from the communication book is that this pre-coding things become very simple. So what I anticipate is some of the like very simple algorithms can be used to handle like the way mobile users are handled for moving for a fixed number of like maybe a less number of base station antennas. If we have a large number of antennas, then we might have a better control of the system because essentially we will not be switching the beam until and unless we know the location. So I'm basically taking the problem from that aspect, that maybe by having more number of antennas we can have a better gauge about the mobile like user, and maybe the dynamic channel change also. But again, these are all speculations. I am not the expert on this, so I think I'll not like say anything that is not very technically correct. But yeah, that is definitely a very important aspect to handle the mobile situation.
So next question is, when you go for massive MIMO, now how will be the isolation between the antennas, and is there a number to it that you can put?
Yeah,
How good the
definitely. So
isolation should be?
yeah, definitely very good question. And I think one of the papers that I suggested that has a very detailed study on this. So the way people look into is they want to ensure this 30 dB isolation, like the papers that I read mostly. So so far the technology that people are trying to build, they are trying to keep the antennas lambda by 2 apart, and that already gives us some isolation. And then by using this polarization diversity and slight twisting of the structure and maybe slight change in the feed network, putting some of these neutralization lines, and there are a number of technologies there. Like so, the number to it is 30 to 35 dB. Now, I would like to point out here is that isolation is another very key aspect for this full duplex technology, because I did not discuss that part during my presentation. But for the full duplex thing, we have to like increase the isolation to like very large value, like maybe up to 70 dB or something, so that later on by using the digital processing, it is enhanced up to this 100 dB, so that that self interference level is killed. So using that, for that case, the number is around 70 dB, and that cannot be done by using the simple decoupling things. So people are trying to look into using the hybrids and some of the other techs to take care of that part, like to analog way it decrease the isolation or increase the isolation rather to that value. But for massive MIMO base stations that I told, that they are mostly around this 30 dB.
Okay. Next is, so when you said that the power required will be less for these MIMO antennas, which means that we'll have to go for more number of base stations. So
Yeah.
how do you relate these two things?
Yeah, so this is also a very good question. Like when we say that the power on one thing will go down, but will that mean necessarily, like there are two things to that. Like one thing is we are talking about when we talk about this millimeter wave systems, then we are essentially trying to make it smaller cells and go with the this like small cell, and number of small cells will essentially increase. But when I'm talking about the sub 6 or maybe the sub 1 range, then I am not sure whether when I talked about the decreasing in the power, I did not really mean that I will go for more number of base stations there, because if I am realizing the higher value of gain over there, then probably I can work with the lower power value to serve the same number of users present in the same number of cells. So I think that is the way, like we probably will not have to, until and unless we go into the millimeter wave frequency range, we will not probably increase the number of base stations that drastically if we are using the more number of antennas. And there is a scaling, like the power required with the proportional to 1 upon square root of the number of antennas they are used. So yeah, I think that probably answers the question.
Yeah, sure. So next question is, so when we go, is it possible to have ultra wideband MIMO systems? And if so, when should be the time domain analysis be done for the MIMO system?
Yeah, so ultra wideband MIMO systems are pretty much there, and I had the chance to work with some of my master's colleagues who did a lot of work on this UWB MIMO system design. And if I remember correctly, some of the works are were reported in some conferences in, I think probably in IEM 2017 or something. There was some of the work that we reported in for UWB MIMO system. So yeah, so the time domain evaluation of this envelope correlation coefficient for that ultra wideband system, that is indeed another interesting research problem. And to do that, essentially what we have to do is we need to model the current on the system for this pulse excited condition, and that is doable. And we are doing some works related to that, but it is slightly slow. And from the time domain, we are also like not only for the far field correlation, we are looking into the near field correlation of the UWB MIMO systems also, because essentially what will happen is for the UWB systems, generally the power level is much low. So, and they definitely will not be used for the base station or all that kind of purpose. So MIMO technology is general and it can be used for any like antenna like configuration, because you can extrapolate it and you can use it for other applications as well. So yeah, I think that that is doable, like time domain analysis of UWB MIMO systems and evaluating the ECC, that is doable.
Okay.
Yeah.
Next question is regarding the expression for the envelope correlation coefficient using the 3D pattern.
Yeah.
So what they have asked is, generally the isotropic environment is considered while calculating the ECC. So what about the other kinds of environment, and how difficult it will be when we take a non-isotropic environment for doing these calculations?
Yeah, so I think this is a like very good question. And I think I mentioned that when we have this isotropic or uniform propagation environment, then essentially we can use the S parameters, and we do not need to use the pattern kind of things, because we have the S parameter based formula, and there are terms with the antenna efficiencies also embedded in that, and that works pretty well. But the challenge comes in when we have some non-isotropic environment, because the formula where we use the S parameter based thing, that does not work for like that is only derived with the assumption of the isotropic environment. So for this non-uniform or non-isotropic kind of environment, we then have to go for the pattern-based evaluation of the ECC. Now here I would like to point out a couple of things. Like when we talk about evaluating the or characterizing the antenna itself, then we have to find out the ECC. But another way to work around is you can actually model the complete system. You can model the transmitter, you can model the receivers, and you can have the channel, and some of that things can be done with the softwares also. And we people in the channel propagation modeling domain, they do that in terms of measurement campaigns. So from that you can find out the data rate, so you do not have to evaluate the ECC in that kind of situation. But yeah, if we want to find out the ECC for let's say non-uniform propagation environment, then you need to apply some of the knowledge of this antenna polarization and antenna patterns, individual radiation patterns. And precisely to solve that kind of problems, we are trying to use this current green function based method, because if we have a knowledge about the individual antenna currents and we can ensure that okay, there is certain kind of port to port isolation is there, then we can extrapolate that knowledge of the individual radiating currents. Like we don't have to go into the patterns because those things are taken care of in our cross correlation Green's function. And in the CGF we can incorporate the non-isotropic environment parameters also. So using that, but that basically bridges the gap between the environment and the antenna radiation or radiating current of the antennas. So using that, you can actually evaluate the ECC in a very easy way. So that is why the research challenge is there, and we are currently working on that. So, and some of the things we have already reported, and we will be extending them. So yeah, that pretty much I think sums up.
Thank you, Dr. Devdeep, for answering all the questions. So final thing, which I have been seeing, receiving a lot of questions asking on the books or the materials to on the calculation about channel capacity and all these mathematical things related to MIMO. So could you just go back to the slides where you had shown all those books or papers?
Yeah,
I think people will be able to take it down quickly. So yeah, participants who have been asking me that question here, you can please take a note of it now.
Yeah, sure. Do that. So yeah, one of the things I think this paper, maybe you can see that this I would like, because this has a summary. That's why I pointed out like this near field cross correlation analysis for MIMO wireless communication. You can download this paper, and in the bibliography of this thing, we have tried to summarize the number of books that are generally followed for like the general capacity computation. One of those things by, I think I'm forgetting the name of that scientist. Yeah, I think Robert Vaughan, from Simon Fraser University. His book reference is there. So this is one thing that I wanted to show here. I think probably that they will be able to note it down. And now I'll go back to the other book. I think, yeah, this is one of the books. This can be acquired. I think this new foundation for applied electromagnetics. Then mostly for the channel thing, I would like to suggest Professor Chokalingam and Professor Sundarajan's book. So I'll bring them to that slide sometime. Yeah, so I think, yeah, here also this is one of the book, like massive MIMO networks, spectral energy and hardware efficiency, foundation and trends in signal processing. And apart from this book, I think by Emil Bjornsson, he's very much active in LinkedIn and other social media, and he, I think, uploads YouTube lecture. He has his channel, so that is also a very good understandable source. And yeah, so this large MIMO system by Professor Chokalingam and Sundarajan. So this one I think also is a very good read. And you can see some of the like topologies of the MIMO base stations also. So yeah, so this is pretty much it, I think.
Thank you, Dr. Debdeep, for a great talk. You started right off from the evolution and you had nicely completed with so many things in such a short time. I have been getting a lot of congratulatory messages from the participants saying that it was a very useful talk, and it shows that we had a full house audience throughout the talk. So that shows how informative and interesting the talk went. So thank you so much for accepting our invitation, and thank you all the participants for staying throughout. And all the panelists here, I could see Chandrakant sir is there, CJ Reddy sir is there, Sugandhi ma'am is there. If you can all just quickly switch on a video, we'll just take a screenshot, which is a group photo here, and we'll close the session. So,
just I want to, the CJ here, CJ Reddy. I just want to make a comment, maybe, I guess, a small comment here.
Yes,
very nice presentation. I enjoyed it. And also, going to the background, I guess, is I met Professor Anter in maybe 1991 when I went to CRC in Ottawa in Canada. So we have some connectivity, I guess, between both of us. Though I never worked with him directly, I normally meet him very often, of course, obviously in conferences and things like that. And also, just to close my comment, I guess, is I know you covered most of the topics very nicely, but of course my talk tomorrow will focus a little bit more on the channel modeling as well in the propagation, urban, rural, and those kind of things. So it's a nice segue, I guess, from your talk to my talk tomorrow. And also, I
Yeah,
like your computational electromagnetics background because that's my background as well. So, thank you very much.
Yeah, thanks a lot for the comments, Professor Reddy, and definitely I'll join your talk tomorrow and learn from it. Yeah.
No tough questions though.
I just want to add something.
Yes, sure.
Dr. Devdeep, nice. Means it is really wonderful talk, and all participants must felt very energetic after listening to you. And amount of content that you have delivered in this one, I was just like it was a football match. Means no time people can take any one. So it was a really high energy octane, high octane this one. So very and to carry forward, it will be followed by CJ Reddy's talk tomorrow, and it is a nice vision. And welcome you formally for the first time. I am getting this opportunity to welcome in the Bangalore section. So that is a pleasure for all of us to have you, and probably have very close interaction with you.
Yes,
and congratulations for your recent Infosys Young Achievers this one. So many things actually. Every time we meet, we get some occasions to congratulate you. That is the energy you have. So with that, maybe we'll have the and we have many persons also joining their meetings, like Madhavan sir. I saw many nice comments they are giving, and today also we could have 220 plus participants. That's a great achievement, and it is continuing, and it will continue. I feel the way you're delivering the vision. So now over to Kirti Priya for your formal closing comments.
So thank you so much, sir. Thank you all of you for being here, and for the participants who have been. I can see still 150 participants are around here even after the Q&A session. So, so participants, tomorrow CJ Reddy sir is giving a talk. So kindly join us. You will be sent a reminder link again in the morning. So make sure to join us at 6:30 p.m. tomorrow. So thank you all once again. Good night.
Thank you. Thanks. Thanks for the nice words, and I would like to look forward for the rest of the things. I'll join and maybe learn many things from them. Thanks a lot.
And yesterday also he was there, so try to look for him and make him elevate him such that he also can offer his comments on the talks.
Yeah.
Thank you. Bye.
Bye. Good night.
Bye. Good night.